Look at three matrices. The first is symmetric with entries 2, 1, 1, 2. The second is diagonal with 3 and 1 on its diagonal. The third is asymmetric with entries -2, -15, 1, and 6. On the surface, they look nothing alike, and yet all three share the same hidden DNA, the eigenvalues 3 and 1. They are secretly members of the same family. Two matrices A and B are called similar if there exists an invertible matrix M such that B equals M inverse times A times M. Invertible means that M has a non-zero determinant, so its action can be undone. This single equation defines an equivalence relation. It groups matrices into families. Every matrix sits inside a similarity class containing infinitely many siblings. They all look different on paper, but they encode the same underlying linear transformation. The matrix M is the translator between perspectives. Change M and you land on another family member. The transformation itself never changes. Only its description changes. Here's the intuition. A matrix represents a linear transformation, but its entries depend on the basis you choose. Pick standard coordinates, and you get one matrix. Rotate your axis, and the entries change completely, but the transformation itself is identical. The matrix M is the change of basis matrix. M inverse times A times M translates A's action into the new coordinate system. Same arrow, different ruler. This is why similar matrices behave identically. They stretch the same directions by the same factors. The eigenvalues, the stretching factors, belong to the transformation itself, not to any particular basis. Diagonalization is a special case of similarity. When we write A equals S lambda S inverse, we're saying A is similar to the diagonal matrix lambda. Rearranging gives S inverse AS equals lambda. Here, the change of basis matrix S contains the eigenvectors of A as its columns, and lambda holds the eigenvalues along its diagonal. Choosing M equal to S produces the cleanest possible family member, a diagonal matrix. For our example, A equals the matrix with rows 2, 1, and 1, 2. Its eigenvectors are 1, 1, and 1, -1, so S is the matrix with rows 1, 1, and 1, -1, and the lambda is the diagonal matrix with 3 and 1 on its diagonal. Lambda is the simplest cousin in the family, but it's just one of infinitely many similar matrices. Let's build a similar matrix ourselves, using a non-eigenvector M to prove this works for any invertible choice. Take A equal to the matrix with rows 2, 1, and 1, 2. Now pick M to be the matrix with rows 1, 4, and 0, 1, an upper triangular shear with nothing to do with the eigenvectors of A. Its inverse is the matrix with rows 1, -4, and 0, 1. Now we'll compute B equal to M inverse times A times M and see what comes out. Let's compute this from right to left. First, we'll find a times M, then we'll left multiply by M inverse, starting with A times M. Row 1 of A is 2, 1. Dotted with column 1 of M, which is 1, 0. That gives 2 times 1 plus 1 times 0 equals 2. Now row 1 of A dotted with column 2 of M, 4, 1. That's 2 times 4 plus 1 times 1 equals 9. Row 2 of A is 1, 2. Dotted with column 1 of M gives 1 times 1 plus 2 times 0 equals 1. Dotted with column 2 gives 1 times 4 plus 2 times 1 equals 6. So A times M equals the matrix 2, 9, 1, 6. Now we left multiply by M inverse. Row 1 of M inverse is 1, -4. Dotted with column 1 of AM, which is 2, 1. That's 2 minus 4 equals -2. Row 1 of M inverse dotted with column 2, 9, 6 gives 9 minus 24 equals -15. Row 2 of M inverse is 0, 1. Dotted with column 1 gives 0 plus 1 equals 1. Dotted with column 2 gives 0 plus 6 equals 6. The result, B equals the matrix -2, -15, 1, 6. And there it is, the same mysterious matrix from our opening frame. Now let's verify the kinship between these matrices. The trace is the sum of the diagonal entries. For matrix A, the trace is 2 plus 2, which equals 4. For matrix B, the trace is negative 2 plus 6, which also equals 4. They match. Next, the determinants. For matrix A, 2 times 2 minus 1 times 1 equals 4 minus 1, which is 3. For matrix B, negative 2 times 6 minus negative 15 times 1 equals negative 12 plus 15, which is also 3. They match again. Since the eigenvalues of a 2 by 2 matrix sum to the trace and multiply to the determinant, both matrices share the same eigenvalues, 3 and 1. The hidden family is confirmed. Why must eigenvalues survive? Here is the proof in 4 lines. Start with the eigenvalue equation. Ax equals lambda x. Now insert the identity m times m inverse between a and x. This changes nothing since m times m inverse equals the identity. We get a times m inverse times x equals lambda x. Next, left multiply both sides by m inverse. On the left, we have m inverse am acting on m inverse x, but m inverse am is exactly b. So the left side becomes b times m inverse x, the right side becomes lambda times m inverse x. Putting it together, b times m inverse x equals lambda times m inverse x. This is the eigenvalue equation for b with the same eigenvalue lambda and a new eigenvector m inverse x. So every eigenvalue of A is also an eigenvalue of B. The relationship is symmetric, so the reverse holds too. Eigenvalues are invariant under similarity. Period. Notice what the proof actually says. Eigenvalues are preserved, but eigenvectors transform. If x is an eigenvector of A, then m inverse times x is the corresponding eigenvector of B. This makes sense. We change coordinates, so directions get expressed differently. The stretching factor stays the same, but the description of which direction gets stretched changes. Don't fall for the trap of thinking similar matrices have identical eigenvectors. They have corresponding eigenvectors related by m inverse. Here's the big idea. A matrix is a description. The transformation is the reality. Similarity is the algebraic statement that two descriptions refer to the same underlying object. Eigenvalues are the basis-independent truth, the property that survives any change of perspective. This is why physicists, engineers, and the data scientists obsess over them. When diagonalization fails, when no eigenvector basis exists, we hunt for the next simplest cousin, the Jordan form. But that's a story for another video.